Antoine is going to talk about elliptic Calogero motor and gauge theory. So please.
Okay, thank you very much. Well, welcome everyone for this second day, and I would like to thank the organizers for inviting me, despite the fact that I have not directly worked with Philippe yet, so this might happen in the future, but at the moment I will present some work that I did some time ago, actually almost 8-9 years ago, and I will tell you why. Before starting, as is customary in this kind of celebration talks, I tried to look if I had interesting pictures of Philippe, but as I said, I did not work with him, so I don't have Philippe doing his favorite activity, which, as we learned yesterday, is computing, but I have him in a very small picture, in maybe the second best activity, which is enjoying I don't know, life, and this is a PhD defense, and maybe surprisingly the third most qualified activity, which is gardening. So this was last year. The roses really needed a trimming, and I think he volunteered to take care of them. So this was nice, and somehow I have this picture in my folders. So okay, so now usually when I have given talks recently, it's been mostly about this kind of pictures, which involve quivers and Hasse diagrams and stuff like that. But for two reasons, I will not talk about this now. The first reason is that I've mentioned some of these topics actually to Philippe in particular in a few little talks that we had last year. So I thought I should pick something else. And also, I think Amihai later today will probably mention some of these things. So and he's the master of this, so I will leave it to him. And instead, I will turn to some much simpler topic, which is particles on a torus. So also, I thought that this would fit nicely with the title of the conference. It is really at the crossroads between physics and mathematics, and there is, like integrable system and combinatorics, yeah, a little bit, and definitely a lot of joy. And I hope that this also will trigger some interest, maybe some surprise from the audience, and well, Philippe in particular. So, okay, so here we go. The problem I want to describe today is n particles on a torus, on a two torus, which interact pairwise. You should think of some kind of electric interaction between them. And my goal will be very, very modest, to understand what are the stable equilibrium configurations of these particles. So okay, here's the torus, and I have n endpoints. So the first thing I have to tell you, of course, is what I mean by interaction. And because we are on a torus, I will consider it as a complex surface of genus 1, and I need a potential which has periodicity. So there's not much I can do. The simplest choice would be to take some potential which decreases, like maybe 1 over r squared. Well, turns out the constraints of periodicity imposes to use elliptic functions, and the most natural choice is the Weierstrass function. So the torus I consider as C, modified by a lattice, tau plus z tau. So the particles belong to this. So they are periodic. And the potential should be doubly periodic. So the most natural choice is to use this sum over the Weierstrass function, which, so the graph is here. So there is a pole, a second order pole at 0. So when the particles collide, this is strongly not favored. And then, okay, it's periodic like this. So that's the potential. And the question is very simple. Take this potential and try to find the equilibrium positions. And of course, there is some kind of translation invariance because it's pairwise interactions which depend only on the difference of the coordinates. And so we can assume that the last, one of the particles sits at the origin. And of course, there is permutation invariance. So, okay, so this is called the Calogero-Moser Hamiltonian. So it's written here. There is the kinetic term and the potential, which is the one I gave before. But since I want to find equilibrium positions, I will set immediately the momenta to 0, and I want to solve these equations, I want to find the stationary points of the potential. So this is extremely simple to do if n equals to 2, and so here is the solution. The potential in that case, okay, as I said, one of the particles sits at the origin, the other one is on the torus somewhere. The potential is just the Weierstrass function, and then the derivatives of the Weierstrass functions conveniently has three zeros, which sit exactly at the half period of the torus. So these are the three solutions that we find. Okay. I must say, I didn't really explain why I'm interested in this topic. I don't come from the community of, say, integrable systems. I come mostly from supersymmetric gauge theory, and I will mention something in these lines a bit later. But for the moment, let's proceed, and let's say that we want to solve this kind of problem where the number of particles is now more than 2. This is when complications will begin to arise.
Question.
Mm-hmm. Do they?
These 3 points, do they have the same energy?
Oh, well, no. So that's a good question. So what we mean by energy, of course, here we have a complex potential. So we can, of course, plug in these solutions into V and compute what this is. And they don't have all the same energy. And actually, I will come back to what the value of this complex energy is a bit later. Yes, there is another. Yeah, of course. Yeah, it's a complexified. So if okay, the question was, it's not very physical because it's a complex energy, a complex potential. So yeah, of course, you could think. Yeah. You could think of these particles as living on a circle, on a real circle, and then you have a real function. The Weierstrass function is real on the real line, but then here I'm just extending it to the torus. So yeah, it's not very physical in that respect. I agree. Okay, but we will come back to this value. Actually, this is very interesting. What's the value of V in these configurations? Okay, but let's first try to find at least the positions. So if you have 3 particles now, the potential, well, you write all the pairwise interactions. Again, one of them is at the origin, so you just have 3 terms like this. And then, okay, you try to solve you take the partial derivatives with respect to Z1 and Z2, and then you find a bunch of equations involving the derivative. And already here, there is a subtlety that arises that there are some obvious solutions to these equations. Okay, now I don't know if I can do it live, but basically if they sit at 1/3 of a period and the other one will be at 2/3 and conversely, it obviously works. But then it turns out there are also some other solutions, but these come in a family. So there is a variety of solutions which are not isolated. And so in order to simplify the problem, I want to consider isolated solutions, which means I consider the Jacobian here, and I want this to be positive. These are the isolated ones. And then there is a branch of a non-isolated one where this thing identically vanishes. And okay, there is another story about this. But for the gauge theory connection, which I will mention a bit later, this, as a spoiler, will correspond to massive vacua of a gauge theory. And that was my original interest. So that's why I want to focus on those. Also, they are much simpler to describe. So with this restriction that this thing has to be positive, we find solutions which, yeah, I think I didn't write because it's basically a generalization of the thing before, where instead of having half periods, you have thirds of periods. And so now you have 4 solutions. And I drew a slightly more interesting case with 4 particles. And then you can really begin to understand the logic. You can align them in various diagonals or like this. And okay, that's what you find. And you see I've disposed that in that way. Here you can start with the 4 particles in this vertical direction, and then you can kind of translate. And it should be clear, if you know the geometry of complex tori, well, complex genus 1 curve, that of course the choice of fundamental cell is irrelevant. And so these different configurations are related by tau going to tau plus 1. You pick a different fundamental cell. So that's why I've organized them in this line. And then there's another configuration here, which is related to that one. And then there's this one, which is alone. And then if you invert tau, exactly, yeah, I see. If you invert tau to -1 over tau, you do a reflection, and then this one will be related to this one, and there is a whole modular behavior of those things. And yes?
But don't you have infinitely many solutions?
No, there are exactly those. If you ask for them to be isolated, so with this condition here, the Jacobian to be positive, they are isolated, and there is exactly this number, 7 solutions.
But if you do your twist, then twist by +1, it closes at some point.
Yeah, it comes here, and then if you do it again,
okay.
now it goes back here. Yes.
It's tau to tau plus 4, for example.
Exactly.
Brings it back.
Tau to tau plus 4 leaves the whole thing invariant. There was another question.
Yeah, so these are unique normal forms, and the general answer is for any n.
Right, I will show the general answer, yeah, just next slide. Okay, so, but indeed, you can already infer what will be the general answer. These are the divisors of 4. You have 4, 2, 1, sum of divisors. That would be the general answer. Okay, so let me just, before giving this answer for general n particles, I want to stress that this is a particular case of a more general system, so that's really the Calogero-Moser potential. Basically, you take the sum of the Weierstrass function evaluated on roots of a certain Lie algebra. If G is SLN, then the roots are precisely of the form EI minus EJ, and so that reduces to the case before. But then you can pick other Lie algebras, and then you will have a slightly different potential. And actually, later I will talk about the D-type, which is actually the reason why I want to show this. This is where I want to surprise you. Okay, so now just to give a little bit of formalism with this problem, we have the isolated equilibria. I call their position ZA. So A is an index to label the position. So here, for instance, A would go from 1 to 7, and it's this set. So there is a finite set, always. And then we can ask about the value of the potential, so the question that was asked before, in this equilibria. So it's a value, it depends on tau, but yeah, and it depends on this index A. And the whole question is now, what is the behavior of these functions? And of course, the Weierstrass function, as we already alluded to before, it has nice modular properties. More precisely, if you have an SL2Z matrix, the Weierstrass transforms this way. It's weight 2. And using this, there should be some of this structure which is inherited by the structure of equilibria. So now I want to ask 2 questions. The first one is how many isolated equilibria there are in general for general Lie algebra. And the second, how do they evolve? So what are these functions? And actually, there is an even more basic question. Is this really a function? This is to think about. And so there will be a surprise about this. The surprise, of course, is that those things, the equilibria, I labeled them by tau, but it's not completely clear that this can be followed as tau varies. So we will see this later. Okay, so now what are the expectations? So now, again, some more formalism before going back to the example. Because of this SL2Z invariant, which is here, we expect that if we have a given equilibrium, and then we perform a modular transformation, then we will reach some other equilibrium. So, and since SL2Z is generated by T and S, which is the action tau goes to tau plus 1, and tau goes to minus 1 over tau, we expect that VA, if I shift tau by 1, it will be V of another index, so T of A. T and S, there are permutations in this set of indices. And the same with S, with a weight 2 here. And therefore, another way of saying this is that if I put all these functions in a vector, we expect to have some vector-valued modular form. And these S and T, they define a permutation representation of the modular group. So these are the expectations. And as we saw on the example, and I will now in the next slide show that this is indeed correct in the SUN case, this is all correct. So here is the solution for SUN. An equilibrium, an isolated equilibrium, corresponds to sublattices of order n in the nth sublattice. So this is exactly what we saw in the previous slides when I showed the n equal 4 solution. You take all 4x4 grids, and then you look for order n sublattices. And it is well known that these can be parameterized by pairs of two integers. D is a divisor of n, and k goes from 0 to d minus 1. So we recover that the number is the sum of the divisors. But actually, there is more structure in here. And if you know congruent subgroups, so this gamma 0 n is the set of all matrices of SL2Z with the upper right entry divisible by n. This set exactly coincides actually with the cosets, these modular cosets. And we can then give, to answer the question, the exact value of what you get if you plug in the equilibrium position in the potential. You get this thing, which is some expression in terms of course, d and k, and the Eisenstein function, E2. So that thing behaves in the way that we expect. And if you, so okay, just to make it clear, okay, in this thing, this is k equal, this is equal 4, and k equals 0, 1, 2, 3, k equal 2 and 1 and 2, and k equals, d equal 1, and we have only 0. And then the way that they are permuted, so these four form a cycle under tau goes to tau plus 1, these two form a 2 cycle, and then S exchanges some of them. You can summarize all this in this kind of diagram. So here the green arrows represent the action of tau goes to tau plus 1. The red arrows represent S. And when there is no arrow, it means that the action is trivial. So that's the structure that we find. Yes?
E2 is quasi-modular, right? So is there a cancellation between the two pieces that give you something modular?
Yes. So the question was, E2 is quasi-modular, and so yes, there is a cancellation. So this is exactly, indeed, a vector of modular forms. There is no...
And if you go to the continuous branch where the Jacobian vanishes, like, do you know if this is also a vector-valued modular form?
Well, now you have... yeah, I don't know. I wouldn't know there how to follow points, because precisely you have a branch, so I don't know.
Okay.
I think it takes much more effort to define, actually, what it even means. Yes, another question here. Wow.
Just once you define the elliptic Calogero-Moser potential, is it real valued? The sum over the group?
No, it's not real valued.
Still not real valued.
It's not real. No, those are complex valued functions.
Thank you.
Okay. So now, the question I want to ask is, what about another algebra? Because I've seen that it's definable for every, say, simple Lie algebra, but I've talked only about SUN or SLN. So what's going on? Yeah, how much time do I have? Not so much. Okay, then maybe I will. I will just mention briefly. This was my the kind of interlude about gauge theory. The reason why I was interested in this. Let me say it very briefly. That there is a supersymmetry gauge theory, which is called n equal 1 star, which is a deformation, a mass deformation of the most symmetric and elegant gauge theory ever, n equal 4 super Young-Mills, where you give a mass to all three chiral hypers. Chiral multiplets, sorry. And it turns out that this Calogero-Moser system, it arises as the integrable system which is canonically associated to this. And you can see it, for instance, from the class S realization, if you know what this means, which is on a torus with one minimal puncture. And from this perspective, and so again, this is where I came from to study this problem, the Calogero-Moser potential arises as really a construction, so that's the physical argument. All the Weierstrass functions arise as instanton corrections. And okay, there is a very nice and long story there, but to me, the bottom point is that these isolated extrema, they correspond to the massive, to the gapped vacua of the gauge theory. And in particular, they correspond to the different phases that the theory can take. Again, if you know what this means, there are some Higgs phases, confining phases, oblique confinement, very rich phase structure in there. And we can exploit actually these ideas to get to the number of vacua, and therefore the number of extrema here. And this uses the theory of nilpotent orbits. Yeah. So just how this arises is that the superpotential in the gauge theory n equal 4 super Young-Mills has this form of a trace of, so these are 3 adjoint valued fields, and the F-term relations associated to this tell you that you need to find 3 matrices valued in the Lie algebra which satisfy the SL2 commutation relations. So in other words, you need to find embeddings from SL2 to the algebra, and these are in one-to-one correspondence with nilpotent orbits. And using this, you can do the counting. And so, for instance, if you want to do it for SLN, then these nilpotent orbits are classified by partitions of n. And if you want to have a massive vacuum, you need the gauge group to be completely broken by these values, which means that you have to restrict to rectangular partitions, those whose Young diagram would be a rectangle. So this is how the label by divisors arises. And then in each one, you have standard results about the number of vacua of pure gauge theory, n equal 1, and that gives this formula. So okay, this was a bit quick, but the point is I want to move on to the kind of surprise, which is what happens if you do this for D-type, or actually any other type, but I did only D-type, actually only D4, because it's very hard. So yeah, let's turn to this G equals SO8 in the last 5 minutes. I copied here the previous slide. I showed you, remember, the expectations. I was saying, yeah, it's natural that if you have an equilibrium at a certain value of tau, if you change tau, you should get another one. So that's still valid, of course. The argument is very solid. However, then I argued, kind of hand-wavingly, that I would get some vector-valued modular form of weight 2, and that then this S and T should define some permutation representations of modular groups. And therefore, if this should be true, then we know very well vector-valued modular forms, so we could expect to have exact answers, and we could expect to solve this problem with SO8 or SON. This turns out to not be true. So this is not vector-valued modular form. They do not form permutation representations. What's the reason? The reason is, well, I will show the reason. First, I explain how I got to these results. So this is, these are results from work with Jan Trost about 10 years ago in the references that I put at the beginning. The idea is we can solve numerically these equations, all the partial derivatives equal to 0. And then you can exploit the fact that the symmetric products, symmetric combinations, symmetric polynomials in the roots should be modular forms in all of SL2Z because they are just permuted. And since the space of modular forms of given weight is bounded and it's really not high, it's easy to perform a perturbative computation to then fix only a few terms in the Q expansion, and then you can find the exact values of these symmetric functions. And therefore, you can find the exact value of a polynomial whose roots are precisely all the equilibria. So this is a polynomial with coefficients in modular form. So there are coefficients in the ring of the ring with integer coefficients generated by E4 and E6, which are the Eisenstein series. And once you get this polynomial, now that's it. You've kind of solved the problem, because now you can look at the roots. You can use techniques from algebra, like compute discriminant, and you can understand the permutation of these roots using some kind of Galois theory on these polynomials. And the idea is you can move on the complement of the discriminant locus, where the discriminant here vanishes, and then when you move tau around, then you can really follow how the roots go. And so you have a map from the fundamental group of the upper half plane minus this discriminant locus to bijections of the vacuum. And okay, now let's jump to the conclusion. The result of this computation is as follows. If you do it for SO8, you find 20 equilibria. That 20 can be obtained from the nilpotent orbit analysis, so that's fine. But then the real surprise is that in addition to the arrows that were shown before, you have this funny blue arrow here, which here I've drawn a kind of a cartoon of the fundamental domain of the modular group. You have the standard actions, so the t, tau goes to tau plus 1, can really be seen as you go to very high imaginary part of tau, and you do this kind of monodromy. And the S transformation is the same around the point I. And usually you have, for instance, that ST cube is also the identity, this is in the modular group, just because you can deform this small contour and this small contour to find a contour around here, and that should be of order 3. But here the big surprise is that there is an additional singularity which appears in the center of the fundamental domain. So something tricky happens here. There is some phase transition, two equilibria collide and give this behavior. So because of this, all these expectations are wrong, because they were kind of assuming that these were well-defined functions of tau defined on the upper half plane, but this is not true. There is a branch cut that connects these 2 points, and this spoils all the modular property. So actually not all of them, because there are still roots of a modular polynomial, but some of them. So the point is, can we understand this? And yeah, so here is a picture of the torus with the D-type model. And well, you have 4 types of colors because we have now 4 particles, but because of the D-type model, you have a reflection particle for each particle. So that's why it becomes a non-trivial model. And somehow when tau reaches a certain value, so when the torus, the ratio of the height to the width of the torus becomes a bit too constrained, then there is a rearrangement of the points. And it's surprising that this happens at a particular value here, which is a constant that you can find exactly. And there is a monodromy when you go around, which is kind of depicted here. And the value can be deduced using this polynomial approach. So it's some horrible function here, but that's the numerical value. And it has some nice properties. So the J, the Klein invariant, is a rational number on this. So it's not really understood what's the general story. But I wanted to emphasize that this problem, which is a very classical integrable system, still has a lot of mysteries in the structure of just the stable positions. And in particular, ST cube, which is equal to 1 in the modular group, is no longer the case. Now you have to do this STM, where you have to also take into account this thing. And it's a new kind of modularity in a sense. And all the Q expansions will have finite radius of convergence. Everything stops here. So that makes the analysis a bit tricky. Okay, so I should now conclude. This problem is very simple to state. From the gauge theory perspective, which is where I come from, it's really surprising that there are these surprises because, again, as I said, the gauge theory is one of the simplest possible that you can imagine with a lot of supersymmetry, and still the structure of its massive vector is not understood because you could ask me what happens for SO10 or some other algebras. The answer is, I think no one knows, but tell me if I'm wrong. So yeah, what happens for other Lie algebras? What's the exact correspondence then between those equilibria and the gauge theory vacuum? What's happening from the gauge theory perspective? What's happening at this point is there should be some kind of phase transition, but I'm not really sure. And yeah, non-simply laced algebra is another thing because now you have several couplings. So all the results that I've shown here are old and they are contained in these papers that we wrote with Jan Trost. But now we are coming back to this with Romain van de Poppelière, Valdo Tatichev, Ricardo Argurio, and we are seeing that there are actually surprises also in the SUN model. So yeah, I think this is a very interesting problem, not very well known, so I think it deserves more. So yeah, I hope you liked it. Thank you for your attention, and yes, happy birthday.
Thank you very much. I noticed that on slide 17, it looked like this rocket of yesterday.
Yes.
So there's a question.
Yes. Could this structure be in any way related to the fact that you can view D as a Norby-fold of type A, right? Like quotient by some automorphism, Z2. You mentioned some Z2.
Yeah. Yeah, probably, but I don't know how to make this precise. I don't know how to obtain this structure. It seems to be really difficult to, but yeah, probably. There is a question.
Do you know the full set of relations between T, S, and M?
Yes. I didn't copy them, but yes, they are in the papers, and yes. So there is a full thing, and you can compute also the order of the group of permutations, which is something like 86,000, something like that. So yes, we know about everything about SO8 case, but that's it. So Romain, that I mentioned at the beginning, is now working on SO10, and then at least we will have 2 data points, and we will see what's going on. But at the moment, we just have these data points, so that's, yeah, we know everything, but that's not really enough to generalize.
Maybe something I did not understand. You mentioned the Calogero-Sutherland model, but you never did anything with the kinetic term. I mean, you just look at the potential. So
that's right. That's why I was always careful to say the Calogero model potential or something. I didn't use indeed the full integrable system, and that's actually, as I said, I don't know so much about it. So there must be some way to leverage all this richness to help us here. But I don't know. So if you have any comments, I would be happy to.
Maybe in the same direction. So you were speaking about equilibrium configurations. Mm-hmm. Can you say anything about correlation functions amongst the points?
So what do you mean correlation functions?
Well, like a 2-point function or something. Because you say it's an integrable system, so it should all be known, right? So
yeah. No, I don't have. I couldn't find a way to use this to solve it, but yeah, there might be something. And there's again, yeah, I haven't. I'm very conscious that I haven't used the full technology. I don't. Again, I'm coming from the gauge theory perspective, where I don't know.
Thank you.
Okay, so
I think there is one.
There is a last question, maybe.
Yeah, the expression for the non-trivial minima reminds me of a famous expression established by Zagier and Eisner-Rigler for the zeros of a Weierstrass function itself, not video related.
You mean?
Is it related or?
This one here?
No, after the penultimate slide, I guess. Yeah, this one.
Oh, this one.
Yeah. They compute somewhere the zeros of a Weierstrass function in the fundamental cell.
Yes, right. So I know this. I don't know how it's related to this, because so here we have.
No, I'm just asking.
Yeah, no. So I know about this, and yeah, I don't think it's related. Here it's read derivatives, and it's. But yeah, of course there might be a relation. I just don't know it.
Okay, I suggest that, okay. One very last question.
Yes, just curious, does ST cube commutes with S and T?
ST cube, possibly. I don't remember. Again, I should have copied the full set of relations. Well, in principle, you can see it here. So you do ST cube. So for instance, ST. Okay, well, here we are back here, but we should involve this somehow. And then you can see if it commutes. So I don't know, we can do it on the figure.
It looks like you have the universal cover of SL to Z.
It should be it should be some kind of universal cover, not the full thing. Of course, then there is some kind of, in the same way as for SUN, there was this gamma 0n. So this was kind of the cover. You had the sum of divisors fold cover. Here you have some cover of order, this number I was telling Michel, 86,000. And yeah, then what I agree. This is the structure here. I don't know how to generalize it to other algebras. But yes, that's exactly the geometry of this thing.
I see. Thank you.
Okay, let's thank Antoine again.
Yeah.